Hello and good afternoon friends, welcome to the CEC live lecture. Dear friends, as you know that we have carried 3 lectures on atmospheric radiation, and through these lectures we try to understand about how atmospheric radiation is caused, what are the reasons behind the cause of the radiations in the atmosphere, what are the elements that cause radiations. Dear friends, today also we are going to talk on atmospheric radiation, and for this we have again with us in our studios Dr. Arun Kumar Srivastav. Dr. Arun Kumar Srivastav is Assistant Professor in School of Environmental Sciences, Jawaharlal Nehru University. So dear friends, let's have a more look on atmospheric radiation. Let's try to understand more on atmospheric radiation through Dr. Arun Srivastav. So first of all, I would like to welcome our guest, Dr. Arun Srivastav. Dr. Srivastav, welcome to the EDISET lecture.
Thank you very much. Good afternoon friends. Today we have the last lecture in the series of atmospheric radiation. Before this we had 3 lectures on atmospheric radiation. We tried to understand the different aspect of radiation, atmospheric radiation, how it is generated, what is the cause of atmospheric radiation, how it is circulated, how it is distributed, what are the different parameters which are associated with the atmospheric radiation. What can be the effects of atmospheric radiation on the atmosphere, whether it is necessary or not, if it is necessary then to what extent it is necessary, and atmospheric radiation should be balanced. This was also one of the important topics in the previous lecture. But the problem is that atmospheric radiation is not balanced. Atmospheric radiation, how much it is coming from the sun side, exactly that much should go away. It should escape from the earth's surface. And in this way atmospheric radiation is balanced. And one more thing is that the outgoing is not continuous, it is not immediate, but it is after absorption into the atmosphere. Thus the atmosphere is kept warm, and because of this time gap between the time gap taken by incoming radiation and the outgoing radiation, the time gap created is very important. It is very important, and it is because these things, this lag is basically related to the flourishment of life, and the temperature is maintained to some extent, a constant temperature. Otherwise the temperature would have been very, very low. It should have gone to the negative temperature and the life would have not been possible onto the earth. On the other hand, in the day period temperature would have been very, very much, and thereby causing, that would have also been responsible for the not possibility of the life on the earth. So the stopping or gapping in the radiations incoming and outgoing time is very, very important. But the problem is that the absorption of radiation by the gases, in fact, which are responsible for this time gap actually, is nowadays not maintained constant, is not in the equilibrium. And because of this equilibrium, disturbances in equilibrium is causing many problems. And one of the major problems is the climate change or the global warming. And this is why the temperature and the increased temperature, how much it should be, it is going beyond that. It is going away of that limit, and this could be catastrophic in the coming years. So in the previous lecture, lecture 3rd, we discussed about how the greenhouse gases are responsible for the trapping of the atmospheric radiation, because the trapping of atmospheric radiation is very, very important. And since the greenhouse gases is increasing day by day because of many anthropogenic activities, and it is continuously increasing, especially after the pre-industrial era. So this increase in gases is being related to the increase in temperature. There is a positive correlation between temperature and the greenhouse gases, and this temperature increase is not good. It is, in fact, it could be very, very fatal in near future, which can be related to many other catastrophes like global climate change, like sea level rise, melting of glaciers before time, etc., etc. So in that context, we will have further elaborate discussion. The temperature, trapping of temperature by the greenhouse gases is also known as radiative forcing, because radiation is being forced into it. So this is called as radiative forcing. today in the final lecture of atmospheric radiation, we will have a discussion on radiative forcing, a detailed discussion on radiative forcing. So, starting from radiative forcing, what exactly radiative forcing is? Radiative forcing is basically it is a change of net radiative flux, short wave and long wave at the top of the atmosphere due to an external perturbation that has the potential to alter global temperature. This radiative forcing is represented by delta F and measured in the units of watt per square meter. This delta F, then it could be represented or given by this formula. Delta F is equal to F net, perturb at the top of the atmosphere, minus F net clean at top of the atmosphere. It says that this is basically the difference between the temperature flux or radiation flux at the top of the atmosphere when the atmosphere is perturbed, when the atmosphere has additional greenhouse gases, minus the temperature or radiative flux when there is no greenhouse additional, there is no additive greenhouse gases, in natural condition. So, whatever the difference comes, it gives the total radiative forcing. This could be positive as well as negative. Now, what is positive radiative forcing? Positive net radiation forcing, net radiative forcing, it is the situation arises when incoming radiation is more than that of outgoing radiation. It implies the warming of the climate system. It implies that short waves are being more absorbed than that of long wave radiation which is going out, and this is also called as positive forcing. Its net result, the final outcome, is in the warming of the globe. What is negative radiative forcing? The situation of negative radiative forcing comes when outgoing radiation is more than that of incoming radiation. Escaping is more than that of incoming, and this is negative radiative forcing, and the result, the net result, final result is in the cooling of the globe. So, positive radiative forcing causes the warming of the globe, and negative radiative forcing causes the cooling of the globe. Now, there is one more parameter that is known as climate sensitivity. Here it is pertinent to mention or explain what is climate sensitivity. Actually, climate sensitivity is the mean change in global temperature that occurs in response to a specific forcing. Whether it is a positive forcing or it is a negative forcing, this can lead to the radiative forcing, and it has the implication on the climate. This is why, because the climate is very sensitive towards this radiative forcing, and this is why it is known as climate sensitivity. Climate models usually predict an approximately linear relationship between the global mean radiative forcing, that is delta F, and the equilibrium global mean surface temperature changes, that is delta Ts. If we have a global surface temperature delta Ts in the units of degree Kelvin, and if we have a climate forcing of delta F in watts per square meter, then delta Ts must have a linear relationship with delta F. So, this is why it is represented here as delta Ts is equal to G0 delta F. G0 is basically a constant, and it is known as climate sensitivity parameter. This basically defines how much deviation could be than that of the linearity which we actually anticipate. This is measured into the watt per square meter. This is measured into the per watt square meter, and it may range from 0.3 to 1.4. Now, here I would like to explain radiative forcing in details. Radiative forcing has many definitions, by the way, or many different kinds. There are four types of in general. There are instantaneous radiative forcing, stratospheric adjusted radiative forcing, zero surface temperature change radiative forcing, and equilibrium climate response. Now, we will discuss one by one what is instantaneous radiative forcing actually. Here we see the temperature profile along the altitude. The temperature is decreasing as we go up or with the altitude, here in this picture as it is shown. and the bottom line or the line at the bottom is, it represents basically the surface or the temperature at the surface, while the line in the middle represents the tropopause, or which is the boundary between troposphere and stratosphere. Here in basically the troposphere, I mean below tropopause to up to surface of the earth, the temperature profile is fixed everywhere. I mean it is constant, what actually should be. And while in the stratosphere or at the tropopause, we will say rather that net flux is not balanced, it is imbalanced. So, here the radiative forcing is, I mean here, and this is a very normal condition of radiative forcing. Now, because I should show that, I should say that the radiative forcing is very significant at the tropopause or between the boundary of stratosphere and troposphere. The anticipated radiative forcing or the general radiative forcing. The next one is stratospheric adjusted radiative forcing. What is stratospheric adjusted radiative forcing? On one side, the blue color represents the normal profile of temperature. I mean initially it is decreasing, then it is increasing, but what is happening in the stratosphere, the temperature is being adjusted. I mean here we can see this red line represents a shifting of the temperature from the normal course, and this is why it is known as adjusted radiative forcing. I mean the radiative forcing is very significant in the stratosphere or above the tropopause, and below the tropopause the temperature is fixed, and in the tropopause and the temperature is constant at the surface, but it is getting adjusted at the stratosphere or above the tropopause. This is why it is known as stratospheric adjusted radiative forcing. Here in the third picture, it is again a radiative forcing which is known as zero surface temperature change radiative forcing. What is here? Blue line represent the same, I mean the normal behavior of the temperature with altitude, while the red line is again changing from top to the bottom, I mean from the stratosphere to up to the surface of the earth. So, the temperature profile is being changed everywhere, I mean in both the layers. So, we can see here that although the temperature at the bottom or at the surface is fixed, it is not being varied, but temperature is being adjusted in both the layers. So, we can say that it allows the atmospheric temperature to adjust everywhere with surface temperature fixed. I mean surface temperature is fixed, but the profiling or the variation of temperature with the altitude is changed to the normal condition. And the fourth one is known as equilibrium climate response. Here the temperature profile is being changed, I mean it is absolutely different than the normal temperature profile, as well as the temperature at the surface is also getting adjusted. I mean it is not the same what exactly it should be. I mean there is a difference in delta S. This is the worst situation. So, we can say here the temperature is shifting, I mean temperature is getting more because it is going towards the right hand side. So, although more or less we will see the pattern of temperature decrease and increase in both the layers is more or less same, but the temperature at the surface or at the ground, which actually it should be, is not the same, it is getting changed, and this is basically the global warming. We can define it as it allows the atmospheric and surface temperature to adjust to reach equilibrium. I mean it has to attain the equilibrium anyhow, and in the process to attain that equilibrium, this surface temperature is being adjusted. And this the adjusted temperature is delta is represented by delta Ts. Now, what are the major causes of this this type of phenomenon? I mean why this delta Ts is, why there is an additional amount of temperature at the surface, even the adjustment of profiling of temperature is there in both the layers, whether it is troposphere as well as the stratosphere. Now, we can understand it with the help of this particular picture. This is one of the components of the causes. I mean the components which causes the temperature increase, this is one of the causes. This is carbon cycle. We should try to understand the carbon cycle. Carbon cycle here, it is given that in we can see 93 billion metric ton is processed by the biological and chemical process through the ocean. I mean, ocean is responsible for the processing of 93 billion metric ton, and it releases by the different biological and chemical process of about 90 billion metric ton. 55 billion metric ton is because of the respiration of human being, animals, etc., etc. And 110 billion metric ton is absorbed by the trees and plants and vegetation, etc., through the photosynthesis. 54 to 55 is released by decomposition. Here it is given, and 1.2 billion metric ton is released by deforestation, etc. 5 billion metric ton is released by fossil fuels or the vehicles, etc. Here it is given. So, I mean, these things should be balanced, but because of the anthropogenic regions, increasing of anthropogenic activities day by day, this cycle is not balanced, and we have around 3 billion metric ton of additional CO2 released into the atmosphere every year. So, this 3 billion metric ton is one of the causes of the atmospheric temperature increase. I mean, in the deviation from the balancing of the radiative fluxes incoming and outgoing. Now, what will happen, how it is responsible for the heating? I mean, the chemistry is given here. We can see if the different radiations, different type of radiation, when it strikes with the molecules of carbon dioxide, what happens? When ultraviolet region or ultraviolet rays of the radiation strikes on the CO2, it basically dissociate the electron or takes out the electrons away from that particular molecule. So, it ionizes it, and when visible light strikes, when visible and infrared light strikes on the CO2, the molecular vibration starts. I mean, molecular vibration is there to some extent, but increases the vibration of the molecules, while the longer wave like microwave, etc., is responsible for the rotation of the molecules. So, but here we should be concerned with the second one, the IR region, because of the increase in IR radiation or infrared radiation, this vibration of the molecules increases, and this vibration of the molecule is basically responsible for the heating of, I mean, this is how the gases starts absorbing or retaining the heat, and this heat is basically, I mean, it works as a reservoir of the heat. It starts working as a reservoir of the heat. It is not only CO2, I mean, here it is given the different component of the greenhouse gases which responsible for the absorption of the radiation, especially the IR. They are CO2, H2O, CH4, nitrous oxide, ozone, and chlorofluorocarbon. Now, we can see here what are the wavelengths which strike upon the different gases to increase the rotation, or when it strikes upon that particular wavelength, then the rotation starts, and I mean, for that particular wavelength, these gases starts working as a reservoir of the heat. So, now we can see CO2 absorbs IR region in the range 4 and around 15 micrometer, while H2O or water vapor absorbs in 2-6 micrometer of the wavelength, while methane absorbs in 3 approximately and 8 micrometers. Nitrous oxide absorbs at 4, 8 and 17 micrometer of the IR region. Ozone absorbs in 9 as well as, I mean, it is a range, not sharp, 9 or whatever number I gave, and 13 micrometer of the IR region, while CFC absorbs in around 9 to 10 micrometer of the IR region. So, these are the gases which are very efficiently, can absorb the IR, and IR is, I think in previous classes we have discussed that IR is mainly re-emitted or released by the earth after getting after earth has absorbed the solar radiation. Now, here we should know, I mean, we should continue discussing, taking example of CO2. The CO2 concentration has increased tremendously, I mean, it is said that there is a 30% increase so far of the CO2 in the atmosphere. We can say here after 1995 to up to around 2005, there is a linear increase in the concentration of CO2. We also have strong observations that there is a strong correlationship between the CO2 and temperature. If the temperature, and we have already I already showed you by how the IR bands or IR regions are absorbed by the CO2 to increase the molecular vibration. Here we can see the temperature has a concentration of carbon dioxide has a strong relationship with the temperature, and as the carbon dioxide concentration is increasing, the temperature is simultaneously increasing. Now, I think we have discussed it in the previous class also, that what will happen if the CO2 concentration has increased significantly. Suppose in 1965 the concentration of CO2 was 320 ppm, and in 1990 it has become 355 ppm. So, using this formula C equal to C0 e to the power RT, we can calculate that the rate of increase of CO2 is around 0.41% per year, but this is not a constant rate, I must mention. This is in an exponential rate of increase, and here if this rate continues, we can calculate time to double when, in what year, in which year the concentration of CO2 will be doubled. With the help of this formula we calculated that in around 110 years since 1990, since 1900, the temperature or the concentration of CO2 will exactly be doubled. So, it will become in year 2100 the concentration of CO2 will get doubled of its value which was there in the pre-industrial era or in year 1900. Now, if this rate and what will happen when the concentration of CO2 is doubled, and with the help of this formula, delta T equal to delta T double upon ln 2 into CO2 T upon CO2 at the initial concentration, we can calculate that there will be an increase of 1.5 degrees centigrade of temperature. During dinosaurs period, the temperature was minus 4.5 degrees centigrade, and in 2100 this temperature will become 1.5 degrees centigrade. And I mean, we can say this, there will be a difference of around 6 degrees centigrade in the last 10,000 years. So, it is this is a very significant and very important increase in temperature. This we have also discussed that human approximately release 6 to 7 into 10 to the power 9 tons of C into the atmosphere per year, 5 into 10 to the power 9 tons due to fossil fuel, 1 to 2 into 10 to the power 9 tons is due to deforestation, 6 to 7 into 10 to the power 9 tons excess, it is excess per year. So, this amount is excess per year. 4 into 10 to the power 9 tons is recycled by ocean and biospheres, while 3 into 10 to the power 9 tons goes into the atmosphere, which is left, which is not recycled, which is additional, and it is happening every year. So, 1 into 10 to the power 9 tons will increase around 0.47 ppm of CO2, and this amount of CO2 is getting added additionally every year into our atmosphere. Now, we will have the case study of CH4. Now, how the concentration of CH4 is increasing. Concentration of CH4 is also increasing every year. It is not constant, and we have the data here in this particular diagram from 1750 to up to 2009. We can see here since 1750 to around 1980 there was significant and constant increase in CH4, but afterwards, after 1980 to 2009, that there is an increase. It is again increasing continuously, but that increase is not that tremendous. There is not sharp increase, but there is a gentle increase. But prior to that, there was a sharp increase in the concentration of CH4. because the sources of CH4 has been shifted, they have been redefined, and the uses is not that much after that particular year, because we have shifted to the cleaner fuels, etc., etc., and because of these things that increase is not that sharp, but still the CH4's addition in atmosphere is there. It is continuously getting added into the atmosphere. What are now we will discuss about some characters of the methane. Methane's natural source is basically decaying of the matters. When any matter after death, etc., whether it is plant or it is animal, flora or fauna, whatever it is, when it dies and starts decaying, then it releases methane into the atmosphere, and this methane has its absorption capacity of IR radiation 25 times more than that of CO2. This is because of this, its global warming potential is 25 times more than that of CO2, and methane is increasing around 1% per year. This methane's increase is directly correlated with the increase in population. Total methane emission is around 375 million tons per year. After carbon dioxide, the next significant contributor in the atmosphere in respect to the global warming is methane. Now, what are the different sources of methane are? Methane has many sources. Here we can see biomass burning it emits around 11%, landfills 11%, domestic savages 7%, animal waste 7%, fossil fuels 26%, enteric fermentation, etc., it causes the maximum, which is around 22%, while rice paddies, etc., release around 16% of methane into the atmosphere. Next one is nitrous oxide. Again, nitrous oxide concentration is also increasing. We can see here in this picture till 1950, from 1750, the increase was not that sharp or that significant. More or less we have an horizontal line. So, there was the concentration of nitrous oxide into the atmosphere was more or less constant, but after 1950 or so, when the vehicular industries they become full-fledged or they start going from house to house, then its concentration in atmosphere has also tremendously increased, and now in year 2030, what data we have, it is at its maximum, which is around 320 ppb, whilst from the beginning, since when we have the data, it was initially 270 and now it is 320 ppb. Some characters of the nitrous oxide, it basically is emitted by fossil fuel burning. It is also released due because of the fertilizers uses. Its addition into the atmosphere is around 0.2% per year. The next one is chlorofluorocarbons. Here we have mentioned around two different type of chlorofluorocarbons, that is CFC11 and CFC12. Here we can see here initially there was no CFC into the atmosphere, but after 1950 the CFC's presence is seen into the atmosphere, and afterwards it has sharply increased till 2000. We can see here CFC is exponentially increasing after 1950, the year when it was included into our day-to-day life. CFC's main source is refrigerators and air conditioners, etc. And because of the CFC, ozone destruction was also started. So, people realized, or the policy makers realized, that it should be banned or it should be stopped. So, after Montreal Protocol, we looked for, or we found the alternative of CFC, and thus we can see here after 2010 the CFC's increase is not that sharp, it is more or less become constant, because we have banned the use of CFC, but still it is present into the atmosphere. One more problem associated with CFC is The other gases what we discussed like CO2, N2O, CH4 etc., it has very short life into the atmosphere, but CFC11 and CFC12 has a very long life in the atmosphere. So, it can remain into the atmosphere for a very longer period. However, we have stopped the use of CFC, or there is no significant addition of the CFC into the atmosphere, but its presence is still there in the atmosphere because it is not getting destroyed due to its long life. Now, we can see here in this particular table that which is given globally average radiative forcing due to changes in greenhouse gases since 1885. Now, since 1885 the radiative forcing of the different gases in the atmosphere has been calculated. Now, we can see here since carbon dioxide's contribution is maximum, so it has maximum amount of radiative forcing, which is basically 1.56, and it is because its concentration in 1985 was approximately 278 ppm, whilst whilst present day it has become 356 ppm, and that is why it has the maximum radiative forcing. Methane's radiative forcing is around 0.47. Its concentration has also increased from 700 to 1714, but its units is in ppb. Therefore, we can say here, and because since it is very less into the atmosphere, so its radiative forcing is is comparatively lower than that of carbon dioxide. Halocarbons radiative forcing is around 0.28 watts per square meter, and it is mostly by CFC 11, 12 and 113. Nitrous oxides radiative forcing is around 0.14 watts per square meter, and it is because its concentration has also increased from 275 ppb to around 311 ppb. Total radiative forcing of these four gases together is around 2.45 watts per square meter. As far as indirect greenhouse or indirect radiative forcing are concerned, ozone is responsible for this. Stratospheric ozone is responsible for around minus 0. It is basically global cooling, not warming, minus 0.1 of radiative forcing, whilst tropospheric ozone is responsible for around 0.4 watts per square meter of radiative forcing. One more thing I would like to say here, that stratospheric ozone's radiative forcing is not constant all the time, although it is given here minus 0.1, but it is averaged over a period. It varies from minus and it is not constant at a particular location. It varies from location to location. So, it ranges from minus 0.05 to minus 0.2 watts per meter square, whilst the tropospheric ozone's radiative forcing varies from 0.2 to 0.6 watts per meter square, and its average radiative forcing is 0.4 watts per meter square. Now, here in this picture, it is nicely represented how much the different components of the greenhouse gases contribute to the radiative forcing of the atmosphere. Carbon dioxide's contribution is maximum, it is 64%, whilst methane's is 19%, halocarbons is 6%, and N2O's is 11%. Now, here in this picture, we will describe again certain other characteristics of those particular greenhouse gases like CO2, CFC, CH4 and N2O. Like present day's concentration of CO2 is 351 ppm. It has an annual increase of around 0.4%. We although calculated 0.47%, so it is approximately 0.4% taken here. And its relative greenhouse efficiency, because relative greenhouse efficiency is taken in respect to CO2, it is 1, and its current greenhouse contribution is around 64%, main sources of fossil fuel and deforestation. CFC, although it has a very low concentration, that is 0.002 2 to 5 ppm, but its annual increase is 5% given here. But the major problem with this is that its relative greenhouse efficiency in respect to carbon dioxide is 15,000. I mean, it is 15,000 more, I mean, stronger greenhouse gas than that of carbon dioxide. Its current greenhouse contribution into the atmosphere is 6%. Its main sources are refrigerators and ACs, etc. The next one is methane, which has atmospheric concentration of around 1.675 ppm and has an annual increase of 1%. Its relative greenhouse efficiency is 25, whilst its total contribution into the atmosphere is around 19%. Greenhouse contribution into the atmosphere is 19%, and its main sources are wetland, livestock and rice fuels, etc. Nitrous oxide's concentration is 0.31 ppm. Its annual increase is 0.2, whilst its relative greenhouse efficiency is 230 and its greenhouse contribution is 11%. Main sources are fuel, fertilizer and deforestation, etc. Now, here we have the we have equilibrated all the different 4 gases what we discussed with the temperature, and we have taken it from the pre-industrial values. I mean, here it is taken from 1985 to, and it is projected also till 2075. We are somewhere in between, or we can say that we are here at 2015. So, now we have some increase of temperature of around 2 degrees centigrade or 1.5 degrees centigrade cumulative, but by 2075, if the present rate of emission of these greenhouse gases persists like this, then we expect that there will be a temperature increase of around 5 degree centigrades in the atmosphere. It is this correlation of temperature with the particular gases are given for all the different gases like CO2, which is having the lower side, which is at the lower side, then CH4 and CFC and then N2O. So, NTO's relationship with the temperature is the strongest, then CFC, then CH4 and then CO2. Now, here the present day contribution of radiative forcing of different gases is represented in this particular diagram. We can see here that CO2 has the maximum again, which is around 1.5, then CH4, N2 and halocarbons. Tropospheric ozone and stratospheric ozone is also given. The blue color bars represent the cooling, whilst the colored like red, orange or yellow or here brown color basically represents the warming of the atmosphere or positive radiative forcing. We can say that stratospheric ozone is causing the cooling, while the tropospheric ozone is causing warming. Here the aerosols total effect is also there, but we will discuss the radiative forcing of aerosols separately. And here at the right hand side we have the net anthropogenic component. It is again around 1.5 or something more than 1.5 watts per meter square, but its range is very high. It is going to up to 2.5. Here one thing pertinent to mention, that linear contrails basically represents the cloud, which is linear clouds which are there. When the planes passes etc., we see a linear line, and that is basically a kind of vapor which has been formed there, and that is also responsible for some amount of radiative forcing, although it is very insignificant, but it causes or it contributes to the radiative forcing of the atmosphere. Again it is represented here, the gases, then ozone, gases, then ozone and different type of ozones like stratospheric and tropospheric ozone, then different aerosols, clouds, etc., how much is positive radiative forcing contribution and how much is negative radiative forcing contribution. So, we can see here that the positive radiative forcing contribution is far more than that of negative radiative forcing. So, ultimately we will have the warming, not cooling. Cooling's contribution, cooling is very insignificant in front of warming. Now, we will discuss about the radiative forcing. So far we discussed about the radiative forcing of different gases, greenhouse gases like carbon dioxide, methane, CFC, nitrous oxide, and some of ozone, tropospheric and stratospheric, although they are not the direct radiative forcing agents, but they are indirect, but they do contribute in the radiative forcing. But aerosols also play, although it is highly variable, but they also do play a very important role as far as the radiative forcings are concerned. They play positive forcing, I mean they contribute to the positive forcing, as well as they contribute the negative forcing too. So, now here we will discuss about the radiative forcing of aerosols. They have both, I mean direct and as well as indirect. What is direct radiative forcing of aerosol? This is due to the direct interactions of aerosol particle with radiations via scattering, absorption and emission, whilst the indirect forcing is due to the clouds, aerosols effect on clouds, and thus we will discuss it, what does it actually means. Thus altered cloud changes the radiation. We will have a detailed discussion about the indirect forcing. As far as the direct forcings are concerned, I think we have discussed in the previous lectures, especially in the first lecture when we discussed about the scattering, reflection and absorption by the aerosols. But now what is indirect aerosol radiative forcing, how it happens and what is there. In this picture we can see here, it is detailed, it is given here the difference between direct and indirect. Now we can see here that on the left hand side there is a arrow in red color as well as orange color. So, some amount of radiation is coming, exactly that amount of radiation is going away, but in the middle picture some amount of radiation is coming, and you can see here the blue encircled line. So, some amount of radiation is getting reflected from there and that is going away, and the remaining portion is coming to the earth. So, this basically is responsible for the cooling effect, because some amount is getting deviated from the top of the atmosphere only. So, this is responsible for the cooling, whilst when the remaining one which is going away after absorption by the surface is again getting deflected, which is encircled here in the orange circle. You can see here the remaining goes away, but some portion is getting trapped or it remains into the atmosphere. Thus, this finally causes the warming of the system or warming of the atmosphere. Now, here it is picturized direct, indirect, and now you can see there are some agents or some aerosols. I mean aerosols are also different types. We have already discussed the sulfate aerosols, soot, mineral dusts, etc., etc. Sulfate aerosols are responsible for the direct forcing, while the clouds etc. are responsible for the indirect forcing, while the soot particles are responsible for the direct radiative forcing. Now, how we can calculate the radiative forcing, especially the direct radiative forcing of aerosols at the top of the atmosphere? We can see here direct forcing of aerosols can be expressed as delta F is equal to short wave forcing plus long wave forcing, where short wave SWF is the short wave solar component of the radiative forcing, LWF is the long wave component of the radiative forcing, which is thermal, and the former one is solar. If we further elaborate here, SWF will become F short wave in the clean environment at the top of the atmosphere minus F short wave aerosols at top of the atmosphere. Long wave radiation is equal to F LW clean at the top of the atmosphere minus F LW aerosols at top of the atmosphere. So, this is how, if we have this short wave SWF or short wave forcing as well as LWF, then finally we can calculate the radiative forcing by aerosols, which is basically direct radiative forcing. Now, what is negative forcing of by aerosols? Aerosols provide negative forcing by reflecting sunlight and by enhancing cloud formation, thereby increasing the reflections. Carbonaceous particles basically soot can provide negative forcing by absorption of sunlight. Aerosols absorptions and reflections are direct effects, while cloud formation and reflection is an indirect effect. We can understand here later on. Now, how this indirect forcing is caused. Indirect forcing, effects of aerosols on the optical properties and lifetime of clouds. Aerosols basically acts as CCN. More aerosols means more cloud droplets. Within fixed water vapor, we have so many CCNs, or we have so many cloud droplets. So, the cloud droplets, although since the number is increasing and the volume has to be maintained constant, therefore, the size will decrease. So, we will have smaller cloud droplets, and more smaller cloud droplets means brighter cloud and longer lived clouds. I mean, the clouds will be more brighter, as well as their lifetime will also be increased, and therefore, there will be more reflections of the solar radiation, and that is why it works as a negative forcing agent. Now, here in this picture we can see here there are two cloud drops. One is a bigger one, and it is basically formed by one aerosol, which has worked as a CCN, and it formed a cloud droplets. But in the same volume, when there were inclusion of many more aerosols, so many more inclusion of many more aerosols, so there were many more clouds, because as much will be the number of aerosols, that much will be the cloud drop. So, the cloud drops number has increased, and therefore, the surface area has increased. Now, we can see although the volumes are same in both the cases, but here the picture which is at the right hand side, the surface area has increased, and therefore, there will be the chance of more reflection of the solar radiation, and thereby causing the negative radiative forcing or the global cooling. Now, here it can be further more clarified by this picture that there were two instances of volcanic eruptions. One was El Chichon and other was Mount Pinatubo, and in both the cases the aerosol optical depth, which is the measure of the absorption of the solar radiation, were tremendously increased. You can see here we are getting two high peaks during both the volcanic eruptions, and we know that during the volcanic eruptions maximum amount of aerosols are released into the atmosphere, and since the atmosphere is covered or it is engulfed by the aerosols, which causes the stopping of the solar radiation, because it is cleared by the increased AOD. So, thus we can say that some of the aerosols do work as negative radiative forcing agent. Here it is a satellite picture, and we can see the amount of smoke which is coming out. Definitely this cause the negative forcing. These type of events are responsible for the negative forcing. Now, the radiative forcing of various aerosol particles have also been calculated. As far as direct aerosols or direct forcings are concerned, they are caused by sulfate aerosols, and it is minus 0.4. It is also variable between minus 0.2 to minus 0.8. Fossil fuel soot, its radiative forcing is 0.1, and it varies between minus 0.3 to minus 0.03 to minus 0.3, whilst biomass burnings is minus 0.2, and ranges between minus 0.07 to 0.6, and total is minus 0.5, and it ranges from 0.2 to minus 0.2 to minus 1.0 watts per square meter. And indirect radiative forcings, so I'm sorry, this was basically of the indirect forcing, and in total its contribution is 0 to minus 1.5 watts per square meter. So, its total contribution is also very significant, and it is around minus 1.5. It represents, this minus sign itself represents the negative forcing or the global cooling but this global cooling or this negative forcing is very less, or it, as far as if we compare it with the global warming or with the positive forcing, its contribution is very low. So, we can say that finally we have a significant positive radiative forcing, and we have collected the data, we have collected the information pertaining to this also, and now it can be seen here in this picture. This picture shows the radiative forcing which is in comparison between the year 1860 and year 2000, and it is at the tropopause or at the top of the troposphere. We can see here the radiative forcing is presented, and the orange color itself represents orange or dark orange, or as much as we go towards the red color, we can see this red color itself indicates the increase in radiative forcing, and the balanced is at somewhere is colored by yellow color, which is not very much here. And in the right hand side of this legends, we will see the blue or light blue or green color, which basically represents the global cooling. And we can see here in this picture, mostly we have the positive forcing more or less everywhere, and some portion which is which comes into the in the category of negative forcing or cooling is represented by is represented by blue or green color. It is somewhere in the African subcontinent, or in the northern Asian subcontinent, or again in the Saharan region, because we know these are the regions where the aerosol particles concentration is very much, because some of them are prominent desert of the world. And similarly here also we have some amount of global cooling. But when we come to the surface, again we will see that more or less the situation is balanced, although cooling is there. And here it is again between 1860 and 2000, year 2000. So we can have idea that here both the global cooling as well as the global warming or negative as well as positive radiative forcing are occurring, but prominently, or it is basically dominated by the positive radiative forcing. So I mean, so far it is I mean, I should end with this note, with this positive and negative radiative forcing. Thank you very much.
With this note, thank you, sir. Thank you so very much for giving us a productive session once again. And so far, we have conducted 4 total lectures on atmospheric radiation. Dear friends, if you want to access these lectures, then there you have YouTube. We are going to upload this lecture very soon on YouTube, so that it becomes convenient for you to see this lecture also. And when you will see these lectures in chronology, it would become easier for you to understand them in depth, in detail. And afterwards, if you have any queries, then you can mail us at info.cec@nic.in. We would be meeting again with a new topic. Till then, take care. Goodbye. Thank you, sir. Thank you so very much.
Thank you very much.